Okay, so far we know what is f of x at time infinity minus f of x theta 0, and the answer also depended on f of x theta 0. So basically, you can figure everything out at the final time after training in terms of what happened initially. So now the question is, well, can we figure out what happened initially? And the answer is yes. That's actually very simple, and it is, again, only depends on k. So this video is about the distribution of f of x theta 0, which is what happens on initialization. So it turns out that if you know what happens at initialization, you kind of know the whole story. So what is it? The answer is it's going to be Gaussian. Why is it Gaussian? It's Gaussian because the parameters are chosen to be Gaussian. So if theta 0 are independent Gaussian parameters, did I spell it right? Independent Gaussian parameters of mean 0 and variance 1, then f of x theta 0. So for any fixed value of x, f of x theta 0 will also be Gaussian. It'll be Gaussian with mean 0, and the variance will be k of x. So that's for a single point. Then for any point x. And you might also wonder, well, what about the covariance? What if, so f of x theta 0 is Gaussian, f of x2 or x prime theta 0 will also be Gaussian. What is their covariance? And that also depends on k. So let me write it this way. If you have 2 points, for any 2 points, if you have x1 and x2, then f of x1 theta 0, f of x2 theta 0, that's a vector that is also Gaussian, and its mean is 0, so it's a mean 0 Gaussian, and its covariance is given by the kernel k again. So you have k of x1, x1, k of x2, x2, those are the variances, and the covariance is k of x1, x2, and k of x2, x1. So if you want to know what is happening on initialization, it's a Gaussian, and no matter how many points you pick, here I did it with 2, in the notes it's written with any number. For any finite collection of points, it's also Gaussian, and the covariance is given by this kernel k. So sometimes people call this a Gaussian process. So a Gaussian vector is something with finitely many components, and a Gaussian process is something where no matter what subset you pick, you always get a Gaussian vector. So some people would write this whole thing, the statement I just said, they would write it as f of x theta 0. They would say it's a Gaussian process, a GP, and they would write its mean. Its mean is always 0. And the kernel k tells you the covariance between points exactly with these matrices. So they would write k of x, x prime to tell you the covariance. So that is the statement, and I think this has a name. It's proposition 7 in the notes. This is proposition 7 in the notes. And there are 2 ways you can look at the proof of proposition 7. In the notes, I did the easy way. So in the notes, the proof of proposition of prop 7 is just follows from a fact about Gaussians, which is that when you matrix multiply Gaussians, you get more Gaussians. So the fact that is being used, and this is called fact 16 in the notes, fact 16, if x is a Gaussian with mean mu x and variance sigma x, then if you set y equal to a plus b bx, where b is some matrix, then y is also Gaussian with mean a plus b mu x, and the variance is b sigma x b transpose. Or is it the other way around? B sigma x b transpose. So when you multiply a Gaussian vector by a matrix, you get another Gaussian vector. And why does that work for us? Because the function f of x theta 0 is exactly equal to theta 0 transpose times phi of x with a 1 over square root of n par. So we're multiplying the Gaussian vector theta 0, which is Gaussian on initialization, we're multiplying it by phi x. And that's just some vector. We're doing a kind of matrix vector multiplication, and by fact 16, therefore f will also be Gaussian. And if you do the calculation and see what its mean and variance are, you get exactly this. Kxx is equal to 1 over square root of n par times phi x transpose times 1 over square root of n par phi x. So that's exactly the BB transpose that appears in this formula. So the BB transpose over here is what gives rise to the kernel K. So that's one way to see it. That's the way it's written in the notes. I will also say it, let me do it another way, which is to write it out as a sum. So f of x theta 0 is actually equal to, and you can write it as a sum, I equal 1 to n par of phi I of x times theta 0I. And for each I, theta 0I is a mean 0 variance 1 Gaussian. What happens when you multiply a mean 0 variance 1 Gaussian by phi I of x? So each term of the sum is a mean 0 and variance sigma I x squared Gaussian. And that's because when you multiply a Gaussian by a constant, the variance gets multiplied by the square of that. So the other way to see the fact that f of x theta 0 is going to be Gaussian is it is a sum of n par Gaussians. Each Gaussian is variance sigma I x squared. What happens when you add up independent Gaussians? The variances add. So each term, the ith term, is mean 0 and variance sigma I x squared. So therefore, the whole thing together is mean 0 and variance. The variance is the sum of the variances. So it's the sum from I equals 1 to n par. The sum of the variances, that's because we're adding up independent Gaussians, phi I of x squared. That's this whole thing, okay, without the n par. And then when you multiply by 1 over square root of n par, the whole thing, the variance gets multiplied by the square of that. So we're using the fact that when you multiply by a constant, the variance gets multiplied by the square of the constant, and when you add up independent Gaussians, the variances add. So if you combine all this, you'll get exactly this fact that the whole thing is mean 0, and the variance is, therefore, f of x theta 0 is mean 0, and its variance is the sum of I equal 1 to n par of phi I of x squared divided by 1 over n par, which is k of xx. So you can do it by this formula, or you can look at it hands-on as sums, and either way you can see that f has to be Gaussian. And with a little more work, and it follows automatically in the matrix vector case, you could get this identity that for any row vector made of f, it's Gaussian, and its correlation structure is given by k. So that is proposition 7, and the last thing you have to do is you have to combine proposition 7, which tells you what is f of x theta 0, with theorem 6, which tells you what is f of x theta infinity in terms of f of x theta 0, and that is theorem 9. So I'll do that in a separate video.